Lastly, let's consider an example with a dependent source. Say we want to determine our Thevenin equivalent for the circuit shown below, where we have a voltage-controlled voltage source. To proceed, we have to solve for open circuit voltage and short circuit current across terminals A and B. We will do this by using a combination of KVL and KCL. This will be employed by removing our load resistance. Now, if we construct a KVL loop around loop 1, we'd have the following. Starting in our bottom left-hand corner and proceeding in a clockwise fashion, we'd have minus 6 volts plus our voltage potential across our 6 ohm resistor, which is expressed as our current I times the resistance of 6 ohms, minus 2 VAB plus our voltage potential across our 4 ohm resistor, which is equal to our current I times the resistance of 4 ohms, and this is equal to 0. Now we recognize VAB is equal to VOC, our open circuit voltage, such that I times 4 ohms is equal to VAB, which is equal to VOC, and VAB within our voltage-controlled voltage source can be represented as VOC. Thus, re-expressing our KVL equation in terms of our open circuit voltage, we have VOC is equal to I times 6 ohms minus 6 volts. Now we need one additional equation. To do such, we will apply Ohm's law to our voltage potential across our 4 ohm resistor. That is, we have I running through a 4 ohm resistor, and our voltage potential across is VOC. That is, I times 4 ohms is equal to VOC, or our current is equal to our open circuit voltage per 4 ohms. Now we can substitute this into our original KVL equation, such that our open circuit voltage is equal to our open circuit voltage times the quantity 6 ohms per 4 ohms minus 6 volts, or our open circuit voltage is equal to 12 volts. Now we have to determine our short circuit current, and to do such we will short terminals A and B, and we will employ KCL at node A. In doing such, we have I1 leaving our 6 volt source and running through our 6 ohm resistor that then heads towards terminal A. We have I2 that branches from terminal A down through our 4 ohm resistor toward terminal B, and then we have ISC going from terminal A to terminal B via our short. We recognize that I2 will be equal to 0, for our current will not flow through a 4 ohm resistor, but rather take the short, such that our KCL equation at node A is reduced to I1 is equal to ISC. Now if we employ this in terms of our node voltages, VC is equal to 6 volts, and VA is going to be equal to 0 volts. For node A is connected to node B via our short, and node B is assumed our lowest potential node. Therefore, our short circuit current is found to be 1 amp. Last but not least, we can calculate our Thevenin resistance as our open circuit voltage per our short circuit current, such that we have 12 volts per 1 amp, or 12 ohms.